Hey, what's up everybody? Welcome back to All for Aero. Today we're going to be talking about a subject that I get asked a fair number of questions on. Questions usually go something like, hey, why doesn't the tractor tip over if I'm driving on a side hill? Or what happens if I drive this truck on an inclination? Is that going to tip over? And so a lot of the questions really deal with what is the stability of the vehicle relative to an inclination or something like that. So they're not specifically asking about the stability, but they're asking actually about the center of gravity relative to the contact points. An easy way to think about this is actually with the human body. So as a human, our center of gravity is actually somewhere around our belly button. So when we stand normally, we stand, I don't know, sometimes shoulder width apart, like my feet are right now. I'm actually stable, right? So my center of gravity is in between my feet, which means I'm relatively stable. So I can move side to side, I'm not going to tip over. As soon as I start to go to a point where my center of gravity is now in line with my left foot, my right foot comes off the ground and I have to balance myself, and then I tip over because my center of gravity moved outside of my contact point. So my contact point being, again, my left foot. So what does that mean for a tractor or for a vehicle? Let's go ahead and dive into that. So here we've got a very interesting drawing. It's a quality drawing of a tractor on a side hill. Now, first and foremost, we've got to define our center of gravity definition. So center of gravity is designated by a circle cut into quarters, and two of the quarters are shaded like so. Okay, so that defines our center of gravity here. Again, as a human, that would be round about our belly button. With vehicles, it's somewhere lower on the vehicle, depending on how the vehicle is constructed. So in this case, we can think about the same thing as what I showed an example with my feet. Our forces pushing up on the vehicle are actually the contact points of the tires. And so we're going to have vectors like that pushing up on the vehicle there. And then the force pushing down is going to be gravity. So gravity is always pushing down. Again, here on Earth, we get to get pushed back down because of gravity. And so gravity is always pushing down. And we'll put that definition here. And so what that means is our center of gravity is the point at which gravity, the force, acts on the vehicle. And so you're going to have a resultant vector of something like that. So you have an angle relative to this inclination angle. And so the point, again, as we described with the human body, is where that center of gravity moves outside of my contact point. That's where I'm going to tip over. And so there are several ways that you can modify that. If you want to become a more stable vehicle, you can do several things. Again, one, you can widen the track width of the vehicle. So in this case, track width is defined as the distance between the two wheels. If we widen that out, now, say we've got a vehicle that has those, so an additional, now I've got a distance from here to here rather than from here to here. So I increase by that much, so you have a much more stable vehicle because I increase the track width. Now another way to do that is to increase the stability is actually to lower my center of gravity. So now if I put my center of gravity, in this case below the axle, and I draw it, I just moved my contact point in a little bit more. And so there are things that you can modify. Center of gravity height, you can change the track width height, and then obviously the easy one is to drive on a different inclination angle. So if I have a steeper inclination angle, this vector is going to have a steeper angle relative to that, which means I'm going to be more likely to tip over. And this is something to be thinking about from a stability standpoint. If you think about a vehicle that has a wide track width, like a car or a race car or something like that, it's got a really wide track width as compared to something like a four-wheeler or a side-by-side. The narrower that track width, the more likely it is to tip over. And so that's something to be very much considering when you're driving some of those smaller vehicles and you drive down a side hill. So with that, that kind of sums it up in terms of the theory behind it. Again, if you have questions, feel free to put those down below. I can talk a little bit more in detail about breaking that vector up and telling you what's happening relative to resultant forces pushing up on the tire, or reaction forces. So I do have an example though, and let's go ahead and jump outside and see if we can really put the stability of our center of gravity into action. All right, we're out in the garage now, and I've got the toy right next to me, but before I do that, I do want to grab something just for safety. Oh, it is, all right. Awesome, okay. Step one complete. Now let's grab the other device. Whoo, all right. Okay, so we've got a unicycle here. And again, one thing to think about is we're trying to show center of gravity and in terms of stability. And so if we look at this, obviously if I let go, it's just going to tip over. Wow, that didn't do it. If I let go and the center of gravity in this point, so the center of gravity of this device, we're just actually looking at the mass of this tube here plus the mass of the seat. And so if we think about the combined center of gravity, it's probably somewhere right about here. And so if this position, if the center of gravity again is going to be that circle that we talked about in the diagram, if that center of gravity is right here, it's going to be relative to the contact patch of the tire, which is right down here where it's touching the surface. So if the center of gravity of this seat tube is in line with that contact point, it should stay upright. Now if I let go, again it's going to tip over. But if I move that center of gravity forward, again the contact patch is at the center of the tire here. Now my center of gravity is outside of the contact patch. It's going to fall over that way. And the same thing if I do it the other way, again the contact patch now is in front of the center of gravity, that will fall rearward. And so when we're thinking about it in terms of how do we ride a unicycle, it's all about maintaining your position of your center of gravity with you on the unicycle. And so you have to keep pedaling in order to maintain your position. So if I'm riding this, my center of gravity is actually going to be above this seat because now I'm sitting on top of it. And so in order to ride it, if I'm going to ride it, I have to maintain my position and keep pedaling along to ensure that I don't fall over. And so if you go too fast with the tire, you're going to want to go backwards. But if you go too slowly, you're going to fall out the front. And so it's all about maintaining constant motion with the feet so that you can maintain your center of gravity relative to the contact patch on the tire. And again, this is going to rotate about the axle. And so it's really easy to swing back and forth. So, well, let's go give it a shot and see if we can ride. All right. All right, thanks everybody for going with me on the ride. Hopefully you enjoyed it and hopefully you learned something. That's what this channel is all about, is learning, experiencing, and using the things around us to understand engineering and education. So if you like that, please feel free to give it a thumbs up. And hey, if you haven't subscribed yet, go ahead. And thanks for going with me again, and happy learning. Catch you later.